introduction. So could you please introduce yourself and talk a little bit about your background?
Okay, so my name is Victory Omole, and I am, so I went to Iowa State for computer engineering. And after that, I got a job here in Ames at Kingland Systems. And I worked there for a little bit more than 2 years as a software engineer. I guess, I don't know if you really know. I mean, I could go really in depth about my background. What else do you want to know about me?
No, I think right now, since you're working in a company, maybe you can talk a little bit about the company. I think the name of the company is SuperTech. So maybe could you tell what you're doing in this company? What's the story of the company?
Okay, so I joined SuperTech last January. And so far, we've been working on writing software for pulse level optimizations of quantum programs.
Yeah, and when you say pulse optimization, I don't think that this concept is very known. And maybe could you introduce the concept? What is it actually about?
Yeah, I'll be happy to. So so there are different level of abstractions that you can specify quantum programs in. So the most common one is the quantum circuit model, which is where you specify quantum gates on certain quantum bits. So, for example, when you want to apply a NOT operation on a qubit, you apply an X gate on a qubit. But what happens is when you send this circuit to the hardware, it gets transformed into pulses. So, for example, in an ion trap machine, where an ion is one aspect of a way that a quantum bit can be described. What happens is lasers you shine lasers on the ions, and then if you shine it at a certain frequency, that applies a pulse on the ion. So that's how quantum gates are implemented in ion trap architectures, superconducting architectures, neutral atoms, and I'm not really sure others, but those are the most popular architectures that ion traps that use pulse level descriptions of quantum programs. Yeah. So what our company does is, instead of interfacing with quantum gates and quantum circuits, we skip that and go straight to the pulses. So we kind of it's kind of like, instead of programming so when C gets transferred to assembly, so instead of just programming in C and then compile it to assembly, we just program in assembly. That's basically what it is.
But then I guess you're using some sort of functioning, right? Because you cannot do it for free, so there is some cost to pay, right, with this approach.
Yeah. So the cost you're incurring is sometimes the calibration. So a calibration is when a gate is pulse level descriptions are calibrated on the back end. So, for example, if I interface with the IBM device and I send a certain quantum circuit, so I send like apply a Hadamard gate to qubit 0, then it goes to the hardware. It goes to IBM's backend, and there they've specified what pulse this Hadamard gate describes. So it's so usually this pulse is sometimes the pulse level descriptions are pretty well optimized, but there are certain cases where the pulses are not as optimized as they should be. So usually you have to compare the default calibrations versus the calibrations you want to send. And also another disadvantage is you are losing this abstraction of gates, which is a higher level of abstraction, which allows you to specify quantum gates quantum programs more generally.
Yeah.
So but we usually don't incur this. But the software we're writing does we do compile gates on our end to pulses. So we kind of take we kind of like move the pulse description side of things from the vendor to us, so we can see if we can make better calibrations.
Yeah. So what you're saying, if I understand you correctly, you're trying to avoid programming with gates. You're addressing directly the hardware. I mean pulses, right? So you don't use gates in your algorithms, right?
So we can describe our algorithms in gates, but the pulses we compile to could be different from the pulses that our vendors compile to, and our pulses are usually more efficient.
I see. And pretty much the idea for that is to work with let's say, with weak quantum computers, which we have today, right? So to boost the possibilities of quantum computers, because now you sort of improve efficiency of quantum computers, right?
Yes, exactly.
So, and in terms of hardware, so do you really care what type of hardware you're using? I mean, ions, atoms, or superconductor qubits, so, or your software is kind of universal?
So our software addresses as much hardware as we want to take care of, and we do need to. I mean, of course, with quantum programs in the NISQ era, which is the noisy intermediate scale quantum era that we're currently living in today, we do need to care about everything about the hardware. We need to care about what implementation it is in. We need to care about the layout and basically everything about that hardware. So our software tries to address all these, minorly significant aspects of the hardware.
Yeah, but it seems like then it becomes slightly complicated in the sense that you have to know about different platforms to really adjust your software for specific platform, right? So then you have to get familiar with different platforms. Or I'm missing something.
Yeah. So that's what we do, right? So then the customer doesn't have to do that. We worry about the differences of the hardware platforms, the layouts, all these complicated things. So all the customer needs to do is just have the algorithm, or even just like not even and then just try it on our software, and then we do the calculation and decide what is the best way to optimize this and what is the best hardware and all those things.
Yeah, I see. I think I get it. And my next question will be, what type of algorithm you're writing and what type of problems you want to address with these algorithms?
So in the NISQ era, in the NISQ era, there's the most general type of algorithms are these variational quantum algorithms, like the quantum approximate optimization algorithms. So these are the algorithms we're focused on, because we're focused on algorithms that are near-term algorithms. So we're not focused on your factoring or Grover search or those faraway algorithms. So yeah, so just basically NISQ algorithms, which is a very a general class of optimization algorithms that interact with hybrid quantum classical algorithms, basically.
Yeah, and maybe could you say a few words what type of team working on these problems, and how many people do you need to write, let's say, algorithm?
How many? Could you be more specific?
Yeah,
about?
so let's say how many people right now in a team of SuperTech?
Oh, okay. So we have. I actually don't know the exact number. So I'm the first full-time hire.
Yeah.
Pranav's the CEO. Fred is the co-founder. And I guess I could go to the website right now and then check, because
sure.
We have about let's see here. So we have Drago, Rohan, Stephanie, Teague, and then me. So yes, so those are the people that are in SuperTech right now.
Yeah, and what say the roles of these people and how you, let's say, separate the task and what's the workflow?
So basically right now it's just me and Pranav because I'm the only full-time hire currently. So Teague is doing his research at Princeton at the moment, and he's the kind of work we're doing is relevant to what SuperTech is working on as well. So
I see. And then and I think the SuperTech is quite young company, right? It's not so...
Yes, it was started a year or two ago.
I see. And let's say the main vision for the company. So what's your plan? What you want to do in the next future, in the coming future?
So yeah, we do want to address this this gap between what quantum computers can do now and what quantum computers can do 10 or 20 years from now. We want to bridge that gap where there's a huge gap between there are really no like algorithms between full-scale tolerant quantum computers and these really small noisy devices.
Yeah, and pretty much I think it's a very good goal because with let's say current quantum computers we cannot address really sophisticated practical problems, but what you're doing is quite important. And do you see that more people, let's say around in different research labs, understand that this approach needs to be taken? Do you feel like support from the community?
Yes, definitely. Most people are aware that it's not a good plan to just focus on building a fault tolerant quantum computer, because there needs to be a certain like feedback loop where you're running algorithms on the computer and then seeing what progress you're making on the hardware, and then just kind of like I mentioned it before. The feedback loop is very necessary. So most people in the community do realize the importance of this type of approach.
So, but when you say feedback loop, could you explain what it means? It means that you're programming something on the hardware, then you see how to adjust the software again to work more efficiently on the hardware.
I'm speaking more generally than that. I'm speaking of like in the case of like, I mean, another approach could be just, let's just put all our resources on getting to quantum error correction and fault tolerance, right?
Yeah.
And not worry about these hybrid classical algorithms, all these these optimization algorithms, these near-term algorithms. So that could be one approach, but no one is. I haven't met anyone who really supports that approach. People are supporting the approach of this approach of trying to kind of do a co-design, right? A co-design between the algorithms and the hardware.
Yeah, and actually, I think the co-design approach becomes more and more popular since people realize that developing algorithm with several millions of logical qubits probably not going to be practical in the coming future, right?
Yes, exactly.
Yeah, yes. So, and this co-design approach, let's say in the SuperTech, you kind of gradually come to this idea, or it was developed before?
Co-design, that's a really good question. I think the co-design approach pretty much started back in like I won't know exactly, because it's been a
while.
It's really hard to like track down like who started it first, right? Because pretty much just like everyone just kind of like accepts it now. I think with like IBM, putting the hardware on the cloud with IBM Quantum in 2016, and then with Rigetti putting the hardware on the cloud as well. I've been hearing about NISQ algorithms since 2015 at least.
I see.
Yeah.
And actually, I noticed that maybe it's a different subject, but I noticed that you have some publication on the Wikipedia when you're trying to explain a few things. So, what's your motivation? First of all, is it correct?
My Wikipedia contributions. That's just something I do for fun. So like it's there's what I found is when I search something on Google and the first thing that pops up is a paper that's 20 or 30 pages long that I have to read through, but I just want to get a certain a simplified concept of what the paper is talking about. So I just wrote a Wikipedia page for it because I would find that useful. So hopefully other people will find it useful.
Yeah, I think you have quite a few posts, and they really explain a few things. And exactly as you said, because sometimes if you have to read the full paper just to get a small detail which you're looking for, it will be quite, let's say, time-consuming thing. So I think it's quite useful.
Yes.
So, and actually, my point is, are you planning to continue this, let's say, activity of making public resources for other researchers?
Oh yes, definitely. I am. I love contributing to the so-called public good, and Wikipedia is a public good. A lot of people benefit from my articles, and I've gotten a lot of emails thanking me for my contributions to Wikipedia. So since I'm getting positive feedback from it, I will continue to do so.
Yeah, I think it's also. And what's your primary motivation to do this? Let's say public good.
Uh, because that's something that I would appreciate if someone did to me. If I benefit a lot from Wikipedia. The physics and the mathematics related articles on Wikipedia are awesome, and I love them, and they really helped me learn a lot when I was an undergrad. So I feel like my contribution to Wikipedia would do the same thing that was done to me, if that makes sense. I'm paying it back. I'm paying it forward.
Yeah, I think it's a good approach. And now when we're talking about, let's say, learning new things, quantum mechanics, of course, and quantum computing is quite complicated. So what's your approach for learning new things?
My approach specifically for learning new things.
Yeah.
Writing. So I like writing, and that's why I write Wikipedia. I also like writing on the quantum computing stack exchange. So I don't learn well from sitting down and reading a textbook and doing the exercises. I learn better, searching for papers and then looking through the papers and trying to summarize what I learned from the papers in my own words.
Yeah, and do you feel like a feedback from the community? Because when you publish something on a stack exchange, I guess it's kind of live, right? So you can get a feedback. Some people could, comment on what you said, right?
Yes, definitely. Quantum Stack Exchange is also an amazing place. I just like the collaborative. It's very collaborative type of atmosphere where you can learn together, build things together.
Yeah, I see. And I think right now the quantum community is definitely growing. So, and do you feel, let's say, support from others in terms of learning or educating yourself?
Oh yeah, definitely. Yeah, everyone's very supporting, especially in the Stack Exchange and a lot of open source quantum projects. Are you aware that IBM quantum the Qiskit, the Circ, the Microsoft QShop. There are a lot of very open source tools and resources and lots of textbooks, lots of tutorials on YouTube. It's just a lot of very important resources to help newcomers learn quantum computing.
And let's say, just for my curiosity, do you think it's difficult for people? I mean, maybe for people who studied physics, maybe they studied long time ago, or maybe they're coming from different background, let's say chemistry. Do you think it's easy to learn programming on these platforms?
That's a good question. I would have to look at the surveys because with Circ we do. I'm also a contributor for Circ, which is a quantum programming language like Qiskit. If people are familiar with Qiskit, Circ is so-called. It's not really a competitor. It addresses. I mean, people could say it's a competitor, but I don't want to get into that. So we do take surveys for users and try to kind of gauge how easy it is to get started and how easy it is to program. Usually, Qiskit has a better. They have more resources to get people started because they have more textbooks, more tutorials. But Circ is working on kind of getting even on that end of providing more documentation and other things. I'm not sure about the Q Shop side of things. I haven't used Q Shop that much to have an opinion on it. But one problem I did run into a bit was trying to install it, because usually most of the programming frameworks I'm familiar with, they were written in Python, so all you do is pip install something. Q Shop is written. It has a Python component, but you also have to like install C Sharp. So I had a bit of trouble with that, but I'm assuming that most Q Shop users didn't. So because they are more familiar with Microsoft's tools. So those are just a small list of programming stuff that I've tried.
Yeah, and you say that you are doing something for Circuit, right?
Oh yes, I'm a co-contributor for Circ.
And how does it work? Could you tell a little bit? So what type of things you contribute?
So Circ, how do I contribute, or what is Circ?
I mean, like, what is Circ, and pretty much both of these questions.
Okay, so Circ is a programming framework for NISQ circuits, so noisy intermediate scale quantum circuits. It was publicly released in 2018, and it addresses most of the NISQ related programming problems. Constructing noisy circuits, simulating noisy circuits, all different types of features are in there. So I definitely recommend that people try Circ as their first quantum programming language.
Yeah. And then how do you contribute to this?
So Circ is on GitHub, so anyone can contribute. There are a list of issues on GitHub that you can go and check out, and then you can make a pull request against the repo, and then we'll review your pull request, and if it's good, we merge it in.
I see. So pretty much everybody could contribute who would like to do this.
Yes, exactly.
But what type of background do you need to really, let's say, work on this package?
So it depends. So if you come from the physics background, you just need to have a basic familiarity with the Python programming language. So there are issues that are more related to people with physics backgrounds, and then there are other issues that you can contribute to if you don't have any quantum computing knowledge. So if you are really good at programming in Python, then you can also and you don't know any quantum computing, then you can still contribute to Circ. So there's a good balance between people who want to, people who lean one way or the other. But over time, the more you contribute to Circ, the more like naturally you gain both those skills, and you can be, that perfect fusion of quantum software engineering.
Yeah, and actually now I'm thinking about a slightly maybe different question, which is when you write a quantum algorithm, do you really need to know, let's say, physics behind it, or you can just maybe be a good programmer and then write the code, or you still have to know a bit of physics?
You don't really need to know physics. You don't really need to know physics, especially like for basic quantum algorithms. If you're learning, if you want to write like Bunsen-Vasarani or Dojo, so there's no physics needed at all. There's just the gates. You can look at the circuit diagram and program that. You can say, oh, I can see that this gate is applied to this qubit, this gate is applied to this qubit, and then this function is called, and then they'll measure it. So there's no physics needed there. But if you want to, the more experience you get in programming, so this is like a introduction, beginner stuff, and then as time goes on, the physics stuff will just you'll just get it by osmosis. You won't have to go out and get a purely quantum mechanical textbooks about Hamiltonians or solving the hydrogen model and stuff. You can just you can just start as a computer scientist and get familiar with the quantum stuff as you go along.
Yeah, and let's say maybe right now I'm getting to my last question, which will be about what do you think will happen with quantum computing in the future? It's maybe a bit of speculation.
What I think will happen? I think quantum computing, I think that it will change everything. But of course, I'm biased, right?
Yeah.
So I think it's a truly revolutionary technology, and it's a technology that I think the 21st century will be remembered for. So like, if in the 23rd century people were like, oh, what happened in the 20th century in terms of technology? I think it'll be quantum computing will be a contender for the revolutionary technology that happened in the 21st century.
Yeah, I think it's a good vision and a good goal. Yeah, I think at this point I would like to thank you for your time and the efforts. So thank you for joining me today.
Okay, thank you so much.